Inverting Opamp. To go over the derivation of the output response of the inverting op-amp, we will review the non-ideal op-amp first. This model here has an input resistance in curly brackets Rn, which in LT Spice, the way I've programmed it, it's 10 mega ohms. Rout is 20 ohms, and the open loop gain is 1 e to the 8th times V2 minus V1, these node names. One thing that this model doesn't do is limit the voltage due to the positive and negative supplies. You could add that in with some if statements, but you can do that later. Now, you can analyze the circuits with the non-ideal op-amp, but it's a lot easier to design, and you get a much greater understanding intuitively of what's going on in the circuit if you do use the ideal op-amp. And an ideal op-amp has the open loop gain as infinity, Rin is infinity, and Rout is 0. And if Rin is infinity, that means no current flows into pin 1, no current flows into pin 2. If Rout is 0, that means Vout equals the open loop gain times the difference of these two node voltages. Now, the idea of the open loop gain being infinity, we'll actually use that later in our analysis. And something to call out, that in LT Spice, a voltage 2, 1 is a shorthand for V2 minus V1. And as we'll find out, that if we choose our resistors, capacitors, inductors, and frequencies properly, we can make these assumptions become true, or they're true enough. So to summarize the ideal op-amp, Vout equals AVOL, V2 minus V1. We set that equal to infinity in our analysis. The current into the negative terminal and the current into the positive terminal is 0. And before we get started, just as a note of shorthand, these circuits are equivalent. Here, the positive pin and these sides of the voltage supplies are all connected to ground. Usually we don't draw the wire everywhere, and we just use the symbol ground here, ground here, ground here, and ground there. And many times we don't even show the power supply. So the fact that this ground and this ground, if you need to help you understand, just draw a connecting wire of 0 resistance between them. So here's the inverting op-amp, and let's find Vout as a function of Vin. Turns out there's one node that we don't know, and that is Vx. And we'll assign the currents and write KCL. And so we have I1 going from the input voltage down to Vx. We have I2 going from X to out. And we do have I negative that I've labeled here. But because Rn is infinite, no current can flow. So really, the original KCL is I1 equals I negative plus I2. But because I negative equals 0, I1 equals I2. So the fact that I1 equals I2 is a direct result of this being an ideal op-amp. Now we use Ohm's law to find the branch currents. So I've assigned a positive to negative and a negative to positive on these resistors. And if this, and that's just an assumption, it turns out to be a good one. The reason why the voltage drops are opposite of R1 and R2, though, is Vout is measured with respect to ground. And so that means R2, this side of R2 has to be the positive side. So I1 equals Vin minus Vx divided by R1, and I2 equals minus Vout minus Vx divided by R2. Something else, Vout equals the open loop gain times V plus minus V minus. Notice we've connected this positive terminal to ground, so V2 no longer exists, and we can simplify Vout equals minus the open loop gain times Vx. Now we're going to find the branch current, and we're going to use A open loop gain as infinity. So here we've re-summarized that Vout equals minus the open loop gain times Vx. We want to solve for Vx equals minus Vout over the open loop gain. And if open loop gain goes to infinity, Vx goes to 0. So now when we look at our Ohm's law equations, I1 is simply V1 divided by R1, and I2 is V minus Vout divided by R2, because Vx equals 0. So since I1 equaled I2, then V1 divided by the R1 equals minus Vout divided by R2, and we get Vout equals minus R2 over 1 times Vin. And this equation, coupled with this topology, you probably really need to memorize, because it'll just take you too long to derive it when you need to use it. So how accurate are these equations? Well, if you download this SPICE file and run it, you'll get these results. And if I have 2 kilo ohms here and 4 kilo ohms there, Vout should equal -2 times the input voltage, which happens to be 1. And the operating point is minus 1.99999. Vx is almost equal to 0. And we can see that the currents between the currents going through R2 and R1, at least for this many digits of precision, are equal. Vout not exactly equaling 2 volts has to do with Rn and a open loop gain that is not infinite. Well, let's look at the non-ideal behavior in op-amp model on the inside. So I've taken this model, and instead of node 2, I have connected it to ground so it no longer exists. And rather than calling this node 1 or the negative node of the op-amp, I've called it X. I've rewritten this equation to minus AVOL times Vx because V2 is no longer there. R out is 20, R in is 500 megaohms, and the open loop gain is 1 meg. And we get the same values. But let's try another example where Vout should be equal to minus 200 volts, because this is 400K and that's 2K. 400k divided by 2K is 200, minus 200. And when I run it, I get minus 1.99.97. And that's pretty close. It is starting to get smaller because, or not, this number is not approaching 200 as closely as the other example, because as R3 gets bigger, there'll be less feedback between Vout and Vx, and the assumptions of the open loop gain being infinite start to fall apart, but it's still pretty close. Well, let's run it with the op-amp model. Vout should be minus 200 volts. We run it, and Vout is minus 14 or almost minus 15 volts. What happened? Over here, our calculations showed that it should be very close to minus 200. Now something has happened here. Notice Vx is 0.92, which is about 1 volt. Vx equaling 0 is not a valid assumption anymore. Well, the thing is V out can't be greater than the power supply. So you can't have a negative voltage that goes more negative than minus 15, and you can't have a voltage go more positive than 15. And in fact, in most op amps, you can't even go up or down to the power supplies. And this is called the output voltage swing, which you can find on the data sheet. Here we have the LM741, and if the voltage supplies are plus or minus 20 volts, you can get plus or minus 16 volts if RL is greater than 10 kilo ohms, and plus or minus 15 volts if RL is greater than 2 kilo ohms. So in fact, we're losing about 5 volts off of the power supply. Modern op amps can get really close to the power supply, but if you want to know how much your voltage output can swing, this is the value to look at. And you can look at that link online. Now, there are some other reasons why V out will not be equal to R2 divided by R1 times V in for the inverting op amp. One is that the open loop gain is reduced, meaning it's not infinity with frequency. This is called a gain bandwidth or bandwidth if you're looking on the data sheet. So a AVOL at DC might be very close to infinity, but it reduces as you go to 1 kilohertz signal, 10 kilohertz, 1 megahertz, 300 megahertz. It keeps going down. Sometimes the output of the op amp is trying to go faster than the op amp can deliver. Op amps cannot deliver an infinite amount of current, and so that can somewhat limit how fast that op amp can change. Just as a refresher, the signal, if you have a signal that will exceed your power supply voltages, you won't get minus R2 over R1. Another reason that we've looked at in the power supply examples is that the resistances have a tolerance. R2 and R1 might not be exactly what we calculated them to be, but also temperature differences and aging can change the values of R2 and R1. And probably the one reason why V out doesn't equal this is that someone forgot to turn the power on. And I just mention it here for completeness.